Okay, let's just revert back to the nonlinear p-centered problem. Maybe you might want to add the word constraint to it, since we are looking at the more general case where you've got these upper bounds as well. Let me just refresh your memory. We have a monotonic increasing loss function associated with each vertex. J is the set of vertex indices 1 up to n. And when you evaluate the jth vertex or the jth function at the distance value between Vj and its closest available center, you get whatever cost is incurred at that distance. And you want your z to be as small as the largest of such costs. There are additional constraints which impose upper bounds on some or all of the distances between vertices and their closest centers. If uj happens to be equal to delta j, then in that case, obviously, such a constraint is not effective. So that's nevertheless, we keep it there. Delta j is the farthest distance from vertex Vj on the tree. If, on the other hand, uj is strictly less than delta j, then in that case, that's an effective upper bound. The case with uj greater than delta j is discarded because in that case, it will not have any effect. All right. And we're trying to find a set of points x in the tree that has p points in it so that these constraints are satisfied, so that the optimum value will be a z value, which we call the p radius for the constraint p-center problem, or constraint nonlinear p-center problem. Okay. Now, last time I told you that this problem can be equivalently stated in this new version, new way. There's a reason why we wanted to do this, even though I did not tell you that before. The reason is because we want to make this look like the regular covering problem that we had dealt with before, so that we can use the covering algorithm actually to solve this problem. All right, so how did we do that? Well, we defined a new function ejz, and we imposed that as an upper bound on each such distance. Now that number, ej of z, for fixed z, if you pick a value for z, it will be a fixed number, whatever ej of z is, and that's going to be a string length in your covering algorithm. That's the idea, even though I did not quite mention that. Okay, so that's what we intend to do. And to justify this, we had to go through some intricate reasoning. Well, it's not really intricate, but all these, the inverses, etc. It makes life a little bit, notation-wise, difficult. Here, the equivalence is established through the following. First of all, you impose z to be greater or equal alpha. Alpha is the largest of the fj0 values. Okay? So when you impose that constraint, z is in the domain of definition of each fj inverse. If it is outside of the domain, in other words, if it's greater than the upper bound of the domain, in that case, fj of uj becomes effective in this minimization operation, so that fj of inverse is always well defined if you pick the argument in the way I stated on the board. Okay? Does that make sense? Okay, so whenever z is greater than the upper bound fj of uj, then this will output fj of uj, and that's certainly in the domain of definition of fj inverse. If z is smaller than that, then in that case, z is certainly less than or equal to fj delta j, okay, which is the upper bound for the domain of inverse function. And it's also bounded below by fj of 0 because of this bound of the alpha bound. So everything is well defined. And the domain of ej is from where to where? From alpha to, or from fj of 0 to infinity. Okay? So this admits every z value in the argument, because you take always the minimum of z and fj of uj. Okay, so with that, we concluded that this is an equivalent problem, except that I must add to this upper problem the constraint z being greater or equal alpha. Otherwise, you know, strictly speaking, they wouldn't be equivalent. But this is a redundant constraint because from previous notions, you already know that the smallest value you get for this problem can never be smaller than the largest of the fj0 values. Do you know that? Okay, yes, you do know that. Because even if you locate a point at the vertex which supplies the value of alpha, you will incur that particular loss, okay? fj of 0. So you can never be below that. For that reason, this is a redundant constraint, so if you append it, this equivalence is well established. Okay. Domain of the function ej is from fj0 to infinity, and ej of z, due to the definition, is equal to fj inverse of z if z is between fj0 and fj uj. And it will be uj, because fj inverse of fj of uj is simply uj. It will be the upper bound uj if z is greater than fj uj. Actually, it also holds at equality as well. Okay. If you draw the function, let me just give you the illustration here. This is the function fj. It goes in some monotonic increasing fashion. And at a particular value uj, you hit the value fj of uj. And you've got your delta j greater or equal uj. So this point is your fj of delta j. And when you look at the ej function, what do you think it looks like? Okay, yes. This function will be the mirror image of this function along the 45-degree line through the origin. So it will start somewhere here. I don't know if I can draw this. Whatever. How does that go? Goes something like this. Okay. I'm not doing a very good job of it, but anyway, you can draw it on your paper. It's supposed to be the mirror image of this along the 45-degree line. So it will look like something like this, even though I did not draw it quite right probably. The value you have here is fj of 0. When you hit the value uj, after that, the function simply goes as a straight line, like this, because it's constant after that. Okay? So it's monotonic increasing up to a certain point. After that, it's simply flat. Constant. Okay. Now, as usual, we want to solve the p-center problem, this version of it, using a sequence of, or solving a sequence of sequence of covering problems. Not set covering, but just covering problems. For the covering problem solution, of course, we're going to use the same algorithm that we've used before. So the related covering problem is the following. You try to minimize the cardinality of x subject to the same constraints There's no cardinality restriction on x. You're trying to locate the fewest possible number of points subject to all of these constraints are satisfied. This is for fixed z. You pick a value for z, and that's for fixed z. So the output will be an integer, a positive integer, as dependent on the value you pick for z. That's your covering problem. So to solve the p-center problem, you need to find the smallest z such that the minimum cardinality for that is how much? Less than or equal to, or less than or equal to p, while any smaller value will give greater than p. So,
something like qz minus epsilon.
Right, z prime is z minus epsilon, if you want to think of it that way. Well, they are the same thing, yeah. Okay. Sometimes I say the same thing in different ways, but they all mean the same thing. Yes? Of which function? Oh, oh, this one. Okay.
Is that inequality or strict inequality?
Well, if you want to be exclusive, it's strict, but nevertheless, it's also going to hold at equality, so I put it down.
Because at that point, F inverse Z is equal to Uj.
Right, when Z is equal to Fj of Uj, then the minimum here will be Fj of Uj, in which case Fj of inverse of that will be Uj. Okay, so it still holds at that point. When you have continuous functions, it doesn't really matter if you exclude or not exclude the endpoints. Okay. Now, here you need to worry about one thing about this comment. The P-center solution here may not have a finite value for Zp. Now, that will be the case if in the original version, regardless of Z, when you wanted to find a feasible set of points having P points in them, if these constraints are not satisfied, if there's no way to satisfy them, then in that case, this portion will actually make the problem possibly infeasible. It depends on the value you pick for P. Okay? If, of course, there's no such X, then it doesn't matter what you do with the above constraint because, it's a futile effort. And so in that case, Zp will be taken as infinity. Okay? There's no minimum. It's an infeasible problem. So how am I supposed to recognize that here? Or can I? If this outputs 0. Are you sure? In other words, is the related... So if you pick a finite Z here, am I going to be able to find a feasible solution to this?
No.
Are you sure?
Yes, of course.
Yes or no?
For any Z?
No, for a given Z. Suppose you picked a particular Z value, finite.
If you could find that, it would be also useful in the first model. So, which means that the first model will have a feasible solution.
Well, actually, no, that's not true. I can pick a Z value here, find a feasible solution. Suppose, let's assume that we can do that. But the cardinality here is too large, okay? It's greater than P. So it's not, it doesn't provide a solution to the P-center problem. However, is it possible for this to happen? That's my question. Yes? No? Yes? Yes. So if you pick a finite value for Z, it is certainly, well, EJZ is a well-defined number. These will be positive numbers because of the definition of EJ. And at worst, if you're not able to do anything, you place a point on top of every vertex. And so in that case, of course, EJ of Z is always greater or equal to 0. In that case, dxVJ will be 0. And so the feasibility here is guaranteed. However, I guess what you said is right in a sense. When you try to make Z smaller and smaller, well, actually, making z smaller will not make any sense. It will it will not reduce the number of points. But making z larger and larger will not reduce your number of points you find to the required number, p. Okay? So, regardless of how large a value for z you pick, you will never be able to get a q of z value which is less or equal p. It will always be the other way. Okay? So that is going to indicate, of course, if you do this in a computation-wise, you may have to try many different z values, and finally you give up. You keep increasing z, and it still doesn't work. And then, of course, you suspect that there must be something wrong here, right? Of course, you don't really want to do that. And so you want to be able to recognize infeasibility in a more straightforward manner. Number two, what kind of z values am I supposed to pick for this? That's, again, a question. Actually, the zp, the p radius value is, again, can be restricted to a finite set of values. So what set is that? So, for any pair of indices s and t, s less than t, let's define the following number. I'm going to call it beta of st, or beta st. It's going to be the minimum of an optimization problem. Minimize z subject to dx vj less or equal uj So x is a single point here. It's a variable point. You are paying attention to two constraints. The first one is the distance of vj to x is supposed to be less than or equal to the upper bound. This is only for j either equal to s or t. So we have only two vertices under consideration. This is a two-vertex problem, even if your tree network may contain n vertices, okay? All other vertices are ignored. The second constraint is simply this one. The loss at the distance between vj and x is supposed to be less than or equal to z for each one of them, okay? So what is this? This is actually the one radius value, constraint one radius value for the one center problem with only s and t, right? So, if the only demand vertices under consideration are Vs and Vt, then your one-center solution will output a certain radius, and that radius is your beta St value. Here are some observations. Beta st is infinity if there's no feasible solution. And when will that happen? It will happen when the distance between S and T is actually greater than the upper bounds, US plus UT, the sum of the upper bounds. Okay? They don't reach each other. If this is not the case, beta st is certainly finite. Okay? And well, let me write it here. Number 3, I'm going to illustrate it using pictures. Beta st is greater or equal the maximum of fs0 and ft of 0. Okay? So these are pretty obvious. Why is this last one true? For the same reason that I told you related to alpha before. Even if you put your point on top of vertex S, you will incur at least a loss of fs of 0. In the other case, it will be at least ft of 0. So whichever one is larger, that will certainly be unavoidable. Okay. Here are some possibilities for solving that problem. Now, usually people have a tendency to define these things in computational ways. Actually, I could have given you a computational way of defining that. However, the gist of the definition lies here, actually. So sometimes if you're in the habit of, as everybody else is, in the habit of defining things in computable ways, sometimes it's much better to avoid that. Just give the definition in the way you actually want it to work, and then worry about the computation later. But usually people don't do that. This is just a sort of a remark in passing. Okay, how do you compute it? Well, what you do is, this is just a graphical way of illustrating it. This is the tree network. Well, actually, part of the tree network, including the unique path between Vs and Vt. Okay? The rest of the tree I don't care about. Now, normally, if I'm trying to minimize the maximum loss relative to S and T, obviously, I want to stay along this path. Now, when I stay along this path, I go a distance of US from Vs, and I go a distance of UT from here. So this one has a length of US, this one has a length of UT. Now, the feasible portion is here, where they overlap. Okay? So at least I know how to identify the feasible part of the problem. And then the question is, where am I supposed to locate here? Well, your function fs increases in some way as you go along like that. So that's your fs increasing as you move away from S. The other one is increasing in a similar way, like this, ft. And what you're trying to minimize here is the maximum of those two functions. So you are trying to minimize this function here, defined by the maximum of those two. Okay? Now, normally if you had no constraints, that would be the minimizing point. And you already know how to compute that from your former knowledge of this course. Yes, it will be a unique point. It is the point where fs of the distance is equal to, so if this is y here, then that point will be defined by fs of y being equal to ft of dst minus y. So you just solve for that and compute what y is supposed to be. Okay? However, here, that unconstrained minimum is not in the feasible region. So what am I supposed to do? In this picture, I move to the closest point in the feasible region. So in this particular case, my minimizing point is going to be that one. That's going to be your y star. And with that, that's going to tell you beta st is actually equal to how much? Yes? Fs evaluated at the distance between Vs and y star. I'm taking that as a point. You may take it as a length if you wish, but just be careful. Don't change apples to oranges along the way. Okay? Which is the same thing as Ft evaluated at the distance between Vt and y star. Okay? Over here, well, let's change that to x. Let's change that to the length because I already took this as a length here. So over here, if you take this as a length, then it's going to be Fs evaluated at y star, which is the same as Ft evaluated at the distance between S and T minus y star. Let's change that. Yeah. Okay. Okay. So at best, you can do as good as the unconstrained optimum, but sometimes your UJs may may require you to move to a closest point in the feasible portion of the path. Okay? Yes?
I do not see how those Fs y star has not the same height as the Ft.
Now, y star is the distance from S to this point you're looking for. Is that what you're asking me?
Yes, but that function of S related at y star should be.
Oh, I see what you're saying. Of course, yeah, you're right. It's actually, sorry. Yeah, you're right. This is greater. In this case, it's defined by Ft. Yeah. Okay. True. Of course, they are not equal. This height is defined by Ft, which is strictly greater than the other one, whenever the unconstrained and constrained minimum do not coincide. Okay? Thanks for pointing that out, because I wasn't really paying attention. Yes. Okay. You've got the idea now. Can you do this analytically? Yes, but you need to know the form of the functions fs and ft. In that case, of course, you can always do these kinds of things. So back to the finite dominating set property. Let's define the set of values R to be the numbers beta st for each pair of vertices. Let's append to it the numbers fj0 So the finite dominating set property we have is the optimal value of the p-center problem is always either in this set or infinity. in the event the problem is infeasible, it's going to be infinity. Otherwise, it's going to be finite, and it will be one of those numbers. So here's the method to solve the p-center problem. I'm going to call the algorithm PrimOpt, standing for Primal Problem Optimization Procedure. Okay, whatever or however you want to interpret it, but it's the primal problem we're talking about. Then there will be a dual problem which I haven't defined yet, and that will have an algorithm called dual opt later. Okay, so PrimOpt is the following algorithm. Step 1, use the algorithm cover to compute the smallest b in the set R for which the covering solution objective value is less or equal p. And parenthetically, let's point out that if Q of B happens to be greater than P for every choice of B in the finite dominating set R, then what is the conclusion? Then the conclusion is there's no feasible solution to the p-center problem. So in that case, ZP is infinity and PC has no feasible solution. Step 2. Well, before I state that, this is the continuation of step 1. Let X solve the covering problem with parameter B, in other words, Z equals B here, assuming such B is found. What B? The smallest B for which Q of B is less than or equal to P. If you make it smaller, it reverses the inequality here. Okay? So if X is the solution for that particular covering problem, then we continue to step 2. We take the P radius to be the B value itself, and we append to X, if necessary, P minus Q of B arbitrary centers If this is not necessary, in other words, if Q of B is already equal to P, then you don't do that. But if necessary, you just supplement it and take the resulting set of points as an optimal solution to the P-center problem. Okay, let's take a 10-minute break now, and we'll start talking about duality. This is straightforward because you've already seen how to do this for the linear case. It doesn't really change for the nonlinear case, as long as you have a covering algorithm working on the side.